Hello everyone, I'm Tongzhang, a student in Research School of Earth Sciences at Australian National University. I am going to share our recent experimental study on the grain size sensitivity of seismic wave dispersion and attenuation in polycrystalline olivine. As we know, the seismic attenuation structure of the upper mantle has been explored by seismologists in both radio model and tomography model, and the accuracy of these attenuation structures has been improved over years. But for all the geoscientists, the ultimate goal is never to obtain a map like this, but to relate the seismological models to the physical chemical states of the Earth interior. Interpretation of the seismological models, like those derived from AuScope-funded campaigns, requires the benchmarking of relevant physical properties in the laboratory, including both experimental measurement and microstructural characterization. This study focuses on polycrystalline olivine because olivine is the most abundant component in the upper mantle. Forced oscillation testing is practiced to olivine sample at elevated temperature to measure their shear modulus and strain energy dissipation at seismic periods. Due to the anisotropic thermal expansivity of olivine grains, the polycrystalline sample is subject to cracking during thermocycling. To minimize the influence of thermal cracking, most of the tested samples are fine-grained with grain size less than 10 microns. However, the grain size for the upper mantle olivine is at the scale of millimeter to centimeter. Therefore, the extrapolation of experimental data towards the upper mantle condition requires a well-constrained grain size sensitivity of inelastic relaxation in polycrystalline olivine, which is the purpose of this study. The pioneering studies in the early 2000s have attempted to constrain such grain size sensitivity, but over the recent 20 years, in order to provide more accurate measurement, there have been a series of updates on the experimental setup, including sample preparation and the design of specimen assembly. Accordingly, such grain size sensitivity needs to be updated by modern measurements on olivine aggregates with various grain sizes. The first step of this work is sample preparation, and we need to find an approach to control the grain size of olivine samples. To avoid complication of natural precursor, we hot-pressed powder prepared from laboratory reagents by the solution gelation method. The synthetic sample has a narrow distribution of grain size and well-controlled chemical composition. Previous studies found that the grain growth within olivine is facilitated by oxidizing hydrous conditions and high temperature. By choosing different metal liner attached to olivine sample, we could control the redox condition during hot pressing and therefore control the grain size of the sample. For example, with the platinum liner attached to the olivine sample during hot pressing, the iron oxides in olivine will be reduced to pure iron and form pyroxene. This process releases oxygen and therefore creates more oxidizing and hydrous condition to promote grain growth. The diameter of the sample is 12 mm, and the precipitation of metal blobs confined to an insignificant rind relative to that. The gap between sample and liner is due to depressurization. Overall, by controlling the hot pressing temperature and the redox condition, we have successfully controlled the grain size of the starting samples. Some grains were plucked out during polishing, especially for the coarse grain samples with high cracking density. After the hot pressing, the samples were fired in controlled atmosphere to restore redox conditions within the stability field of ferrous iron-bearing olivine. Then the sample was assembled like this for mechanic testing. As I mentioned before, to simulate seismic wave propagation in lab, forced oscillation testing has been practiced on polycrystalline olivine. The olivine sample was wrapped by a nickel-70 iron-30 liner to control oxygen fugacity, sandwiched by alumina torsion rods, and ejected by a steel sleeve. Such a specimen assembly was firmly attached to an elastic element within the apparatus, achieved by high confining pressure in argon. Torque oscillating at seismic periods is applied from the bottom of the apparatus, and the torsional displacements of the heated specimen assembly and the elastic element were measured during the fossilization testing. Comparing the raw data with the torsional displacements of a reference assembly containing a sapphire control specimen, we obtain the shear modulus and strain energy dissipation of the olivine sample within a broad seismic period band. We have tested two samples with grain sizes at 7.5 micron and 21.8 micron. The grain sizes of tested sample were determined accurately by EBSD mapping. Here are the experimental results. The two upper plots are shear modulus against log oscillation periods with temperature color-coded, and the lower two are log strain energy dissipation plotted in the same way. The variation of the two datasets is similar. The period dependence of shear modulus and strain energy dissipation both increase systematically with increasing oscillation period and increasing temperature. The sample with smaller grain size is apparently more dissipative, and its modulus is more strongly temperature and period dependent. So we are observing the results of grain size sensitive and elastic relaxation. The next step is to quantify such sensitivity. For the two datasets we have so far, we use a Burgers model with a suitable distribution of relaxation times to fit the shear modulus and dissipation data pairs. The model consists of three components: a spring in series with parallel combination of a dashpot and another spring, following another dashpot. The three components refers to instantaneous elastic strain, time-dependent and recoverable anelastic strain, and temporal but irrecoverable viscous strain during application of a constant stress. When we applied sinusoidal stress to this system, due to the existence of inelastic components, there will be a phase lag between stress and strain. Such a phase lag is manifested as strain energy dissipation. When the period of applied stress becomes longer, there will be more time for the increment of anelastic strain, therefore shear modulus becomes period dependent. In practice, Laplace transform of the creep function of this model in time domain allows us to fit our data in period domain. On the right is a schematic plot of the model in period regime. The anelastic behavior of polycrystalline olivine requires a distribution of relaxation times giving rise to both monotonic background and the superimposed dissipation peak. The dissipation peak is centered at relaxation time tau p, portrayed by the green line. The dissipation background in blue is bounded at tau L and tau h. The upper limit, tau h, is equal to Maxwell relaxation time tau m to ensure a smooth transition from anelastic relaxation to viscoelastic relaxation in orange. The sum of the three inelastic components forms the total dissipation we observed in experiments. The corresponding relaxation in shear modulus is calculated simultaneously. The main character of this study, grain size sensitivity, is separately introduced as MA for tau L and tau P during the onset of anelastic relaxation, and MV for the relaxation times in viscoelastic regime. The details of the model can be found in our recent publication. Such a model with embedded grain size sensitive relaxation times was fitted to the shear modulus and dissipation data for both specimens. In this case, MA is equal to 1 and MV is equal to 3. To more accurately constrain the grain size sensitivity, we will soon test another sample with much closer grain size. The coming results will enhance our understanding of anelastic relaxation in olivine and allow more robust interpretation of seismic wave dispersion and attenuation in the upper mantle. Here are the preliminary conclusions for this study. Thank you for watching.